Hello, and welcome to another brief video lesson on CCD filters overview. All CCD cameras collect one thing, photons. They convert these photons into counts on a pixel. So all you end up with is a file that says, in this pixel location, I had so many counts, so many numbers, and that will ultimately represent an image. So your CCD camera, in essence, is a photon recorder. To get information from our target and to make color pictures, we use filters. These block certain electromagnetic wavelength band passes. And remember from our past lessons, electromagnetic wavelengths are light. So they block certain light depending on your needs and allow other light to go through. So I've got an example here of on the right of the electromagnetic wavelength from that particular lesson. And what we have is the spread of colors with various nanometers, from 400 to 750 nanometers, from the almost ultraviolet, purple, all the way to the longer wavelengths, near infrared. So a filter looks at this swath of light and it blocks certain areas out to allow only certain kinds to go through. So they have a direct impact on electromagnetic radiation and reception by you. They allow us to separate and isolate that incoming light. This allows measurement of the spectrum for various astronomical objects at well-defined points. So if we want to measure something that was very blue and we wanted to see its output, we could use a blue filter that blocks everything out except that blue portion of the electromagnetic radiation. Using filters can be valuable, but in some cases, they are going to permit less signal to get to a CCD chip. So to counter this, you may need to have longer exposure times. It is a trade-off. For example, let's say you have a really faint object and you want to measure it in red or yellow, different kinds of filters. If the object is faint and you start eliminating a bunch of other light sources, a very small amount of photons are going to get through. To counter that, you have to bump up your exposure time to let more photons come in. That's how we can look at filters, how we have to do a trade-off with them sometimes. Filters come in a variety of kinds, but for scientific value, we stick to standardized filters. When you work with brief, all you will use are standardized filters. Now, there are times when unfiltered observations are useful. One of them is where all wavelengths are equally bright. Hot objects, cataclysmic variables, for example. You can just use either an unfiltered or what we call illuminance, which the luminance is really a combination of all of these. It opens itself to the entire visual light spectrum. Or when the object is very faint, you'll need all photons to reach the CCD camera, which we just talked about. For your work with brief, we will only use standardized filters. And here they are. We have two primary filter sets. One is called Johnson and Cousins. And this was derived from an old Johnson & Morgan UBV photometric system. What does that mean? This means ultraviolet, blue, and visual. Visual also means green. Think of them as one and the same. This is why over here, visual is represented by a green graph. It lies in that part of the eye's visual spectrum. So they had standardization for ultraviolet, blue, and green. And they could do subtractions, and you can do this with stellar types. This is an overview. I'm not going in great detail, where you can take the magnitude of a star shot through a blue filter and shot through a V filter, and by algebraic equations, you can find out what kind of star that is. Really cool stuff can happen with filters. The same you can do with ultraviolet and blue. Now, Cousins came along and said, hey, we need filters in the red side, the long side of light. So it came up with the R, the red, and the near infrared passbands. They have the subset C to identify them as cousins, and you can see that right here. So together, the whole set is Johnson Cousins, U, B, V, R, and I. Now, even though the C's are there, we just don't talk about it. So UBVRI is how you will hear mentioned the Johnson Cousins system. Well, one of the keys I want you to look at here is the ultraviolet and the blue, as with all of the other wavelengths, they have areas in which they overlap each other. They're not tightly defined in their band passes. So you have certain wavelengths of lights that'll be visible in both. Well, along comes Sloan. Sloan was a digital sky survey that was accomplished last century, and they defined a new set of filters. And these are lowercase to differentiate themselves from Johnson and Cousins, and they have a prime. All we will refer to these at are U, G, R, I, and Z. They were primarily used for galactic surveys, but they're very useful for stars. Now, U is the ultraviolet, G is the green range, R is the red, I is near infrared, and Z is the deep infrared. The neat thing about these is if you look at the bandpass cutoffs, they have extremely little overlap between them. The Johnson-Cousins system has a lot. The Sloan have very little. This makes it really functional for scientific research. We, the brief system, have Sloan filters. This is an overview to kind of show you where they cover in light. So if you take the Sloan G, that basically encapsulates the area of light that the Johnson-Cousins uses for B and V. Interesting. The U is roughly the same. The R is almost the same. But the Johnson and Cousin I is covered by two different filters on Sloan. So each one of these filters cover different sections of light, and we use that to our advantage. Here's an example. For a given star, its temperature, if you remember, determines its color. The hotter the bluer, the colder the redder. So if I'm shooting an image, let's take a double star case really close, and I want to filter out some of that light so I can try to separate and see these stars, I can use a filter. So in this case here, we use a V filter, and I blocked out all other light. And all that comes through that filter is that green light. Then I can measure it. Even though the source is giving light throughout the visual spectrum, and as you know, beyond the visual spectrum, we are limiting to what's captured to only this particular bandpath, and that is extremely useful to us as scientists. Look at these images below. Two images of the same system, the same star. This left one is a luminance filter, and luminance filter is all of the visual bands, blue, green, red. It's all of that. It encapsulates that light. As you can see, you have many different stars, and they're brighter. But the same picture, the same exposure over here was done in red, where it only allowed the red light to come through. Look at the differences between the two images. Many more stars brighter in the left than you have in the right, but the right is only giving you light from the red. Another filter type is hydrogen alpha. Hydrogen alpha, as this graph shows, of this entire visual band, which is about right here, this is the visual band, is an extremely narrow area of light that is allowing to come through. It's at the 656 nanometer location. It is one line of light. And so what it allows you to do is it allows you to take something like this, where there's an image there, believe it or not, but it's hard to see. And when it only looks at the HA light, what it receives is that hydrogen alpha emission coming through. So all of a sudden you can see something that wasn't there because you used a filter that looks for only a specific area of light. So in summary, all objects produce light through the electromagnetic spectrum. We know this, we understand this. We use filters to manipulate that light. Only allow certain light to come in. Get rid of the other light. Very useful for us in exoplanets, in photometric work, eclipsing binaries, in pretty pictures if we want to make beautiful pictures of galaxies, because cameras are black and white. But what we can do is we can shoot one in blue, one in visual, one in red, and we can take those three colors and combine them into pretty images. Filters are our friend, and we will use those a lot in the course of work with Brief. Appreciate your attention. We'll see you on a future Brief video lesson.